This video is about horizontal projectiles, and before we begin, if you added two vectors, 30 meters per second and 50 meters per second, what is the maximum and minimum resultant vectors? Go ahead and pause it and see what you can get. Okay, there's really many ways you can add vectors, but the one that's going to give you the maximum amount is adding the two vectors head to tail parallel to one another. So if we add the 30 to the 50, you get 80 meters per second. On the other hand, if you added them anti-parallel, one going one way, one going 180 degrees from that one, when you add those two vectors together, you get a minimum of 20 meters per second. So the maximum and minimum is between 80 and 20 meters per second. Today, in this video, what we're going to do is analyze projectiles and describe some important features of projectile motion, and then we're going to try to solve some horizontal projectile motion problems. Okay, before we begin, I do want to give another shout out to my favorite physics website, and that is physicsclassroom.com. If I ever get a chance to meet this guy, I'd shake his hand because this is a website that's one of the first that I've ever seen with physics, teaching physics, and it's pretty useful. It helped me learn physics when I started a long time ago. So let's take a look here, and one thing we can notice is if you look at the green ball, it's going horizontally. And the spacings between those green balls are going to be the same every single time. And then if you take a look at the red ball, you can see the spacings are getting larger and larger and larger as we go along in time. So with all these problems, what we're going to do is we're going to assume there's no wind resistance. And when we do that, we can find that the speed in the x direction is being constant. That's because there are no forces acting in the x direction. However, there is a force of gravity acting down in the y direction, so we can say that the object in the y direction is going to move with a constant acceleration of g. Again, don't make this mistake. G is not gravity. It is an acceleration due to gravity, and we'll learn why that is later on when we start dealing with forces. So for right now, g, it's going to be pointing downward at 9.8 meters per second squared, and because it is pointing downward, we'll say it's negative, because it's an acceleration. Taking a look here, we can see if a projectile is shot, perhaps maybe from a cannon, and it's shot horizontally, notice the line of vectors going in the x direction, or the vectors in the x direction are all going to be the same. That's because our velocity in the x direction is going to be constant. Now in the y direction, we notice that the vectors are getting larger and larger. Now I want to point out here in the physicsclassroom.com, the term speed is used interchangeably with velocity, which is nothing wrong with that. But here in my class, or when I teach students, I want to make sure that we understand that in this case, these numbers here are positive, but technically because the velocity is pointing downward, all of our velocities in the y direction are also going to be negative. An interesting thing that we can do, if we ever had a chance to do this realistically, is if I have a truck and it's traveling at a constant velocity and it shoots a projectile straight up, what's interesting is that the projectile will land back into the place where it was shot. But again, we have to assume there's no wind resistance. And the problem with doing this in a real world is that there's always wind resistance. So this is an ideal situation. But when we deal with physics, we do deal with ideal situations all the time. Projectile motion is one of those times. Because when we add in wind resistance, it gets a little bit more ugly, and that's when you have to resort to calculus. Okay, if I got a plane here, and it's going to drop something, a cargo, a bomb, a chicken, doesn't matter. When objects are dropped while traveling horizontally, what's interesting to note about this scenario is that the object will remain under the traveling horizontal object. So we've got our plane, it's traveling at horizontal velocity, that's constant, and the object that's being dropped is exactly under it the entire time. Okay, so here's some things to remember. First of all, we want to remember that there is no force acting in the x direction. Because there are no forces acting in the x direction, there's going to be no acceleration in the x direction. So all of our problems can deal with a constant velocity in the x direction. The initial velocity is going to be the initial velocity in the x direction. So if you shoot something horizontally or throw something horizontally, the velocity given in the problem is your initial velocity in the x direction. And I've tried this and showed this in my class that if you push an object horizontally and drop it, and then drop another object, they're both going to land at the same time. So therefore, what you can say is that the initial velocity in the y direction is going to be 0. And as always, if we're on Earth, the acceleration due to gravity is going to be in the y direction at negative g. So here's our ugly, ugly equations. Remember, the ones on the left are the ones that govern the x direction, and the ones on the y deal with the y. These are our kinematic equations that we learned earlier. And to be honest with you, the only ones that I give you on exams are the first ones in the x direction. Your job is to make sure that all of these can be transferred over to the y direction by just simply understanding that we've got a negative g here. Okay. So going back to those things to remember, we can say that there's no acceleration in the x direction, so we can eliminate all of this ugliness right there. And then what we can also do is, because there's no initial velocity in the y direction, those terms get eliminated as well. And so what we're left with this equation here is that our final velocity is equal to our initial velocity. Same thing here, our final velocity squared is equal to our initial velocity squared. Those are obvious statements, so we don't need them as well. So what we're going to do with all these equations is reduce them to these ones here. And this is the only equation you're going to need for all projectile motion problems. So we've got our change in position is equal to our initial velocity times time. This is it. Now the other ones in my y direction are going to be the ones that we can use. But for right now, this is it. Okay, it simplifies the problem so easily. Now this is only applied when we use initial horizontal projectiles. When we shoot things at an angle, that's going to be a different situation. We're going to have to change the equations again. So let's take some steps to solve these problems. And I want you to follow these steps every single time to ensure you're going to be successful in these problems. Number one, you'll want to draw a picture to help you what's going on. We are all visual learners here to some extent, and we have to see it. And then once we see it, we understand it. So drawing a picture will help. Number two, you want to define a coordinate system and define where you're going to put the origin. And in our coordinate system, whatever you define as being positive, stick with that, and that'll give you the answer every time. You want to identify your knowns, basically what kind of information can we get out of the equation or out of the word problem, whether it be shown or hidden, and identify, well, what's the question asking me? We're going to call those our unknowns, and then we're going to identify some equations that we can use. And then we can methodically go through each one of them until you've found the one with just one unknown variable. Then you do the algebra, and then once you do the algebra, you plug and chug and solve for the problem. So let's get an example here. So we've got a movie stunt driver on a motorcycle, speeds horizontally off a cliff, a 50-meter cliff high. How fast must the motorcycle leave the cliff top to land on level ground below? 90 meters from the base of the where the cameras are. Okay, so we're going to ignore air resistance, and I'm going to draw my picture. And what I've decided to do for this particular problem is the point at which the motorcycle leaves the cliff, I'm going to define that to be my origin. And if that's going to be the case, if I go down, I'm going to have a negative y direction. If I go over, I'm going to have a positive x direction. So from over there where the motorcycle lands, I've got my final position to be 90 meters away, and my y is going to be negative 50 meters. I'm going to tell you, this is the most common mistake that I see when students do these problems, is that they forget that the change in position in the y direction is negative. You started up here, you end up down here in the negative direction. And I can see here I've got a negative 50 here, which doesn't make sense with my drawing here, but I'm going to continue on. We can fix that later. So here we go. We've got our knowns. I'm going to say that it's 90 meters and negative 50 meters to be our x and y. With our unknown, we've got our initial velocity in the x direction. Well, we don't know what that is. And so we can go ahead and say our first equation, because I have an x here, I have the only equation I can use for the x direction. And let's go ahead and see if that works for us. All right. Well, the problem here so far is I don't know time. And I've got time here, but I don't have it here or anywhere else in the problem, so that might be a problem for us. So let's go through our checklist here. Because I have a y here, I can see that, well, maybe there's going to be a y equation that I can use as well. Let's go through our check marks. All right, so what I do is I put a check mark over everything that I know. I know x, so I put a check mark there over my delta x. I also know that my y is -50, so my delta y is going to be a check mark as well. Then I put a question mark over what I don't know here and here for the time. And then when I do this, what I can recognize is that in this equation here, I have two unknowns. So I can't use this one right away, but I can use this equation here because there's one more bit of information that I know, and that's g. So I have everything that I know except for one variable. This tells me right away that I can use this to solve my problem. And guess what? If I can find the time in my y direction, I can plug that same time into my x direction to give me the time, and then I can finally solve this problem. So there's the equation we're going to use. Let's start off here with, I'm going to go ahead and isolate the time. So the first thing I'm going to do is I'm going to multiply both sides by the reciprocal of -1/2. So I've got -1/2 over here. I'm going to multiply it over here, and then I get rid of my terms. And moving on, so I have -2 delta y is equal to gt squared. Next, I want to get rid of this g and isolate that t squared there. All right, so I'm going to divide both sides by that g, cancel my like terms. What I do to one side, I do to the other. And now I'm left with -2 delta y over g. And then if I take the square root to both sides, and now I'm ready to put in my numbers because that's going to end up being t. But if you pause for a second, wait, hold on, time out. Mr. Watson, how come you have a negative here, and if I take the radical under a negative, I'm going to get an imaginary number or a nonsense number? You're absolutely right. I 100% agree with that statement. However, remember, our y is going to be negative. So if I multiply a negative by a negative, this cancels out to become a positive, and so you're still on the right track with the time there. Okay, the next step is our plug and chug, and I get 3.19 seconds for the time. Okay, so I can add that to my knowns, and when I do that, I've got my time, I've got my change in position, or in this case, it's going to be x. From here, I can solve for my initial velocity. And I divide both sides by time. Next is plugging and chugging. And by the way, before we plug and chug, you should already know this equation, which is our velocity is equal to our change in x over change in time. But I went ahead and eliminated my initial time because it's my independent variable. And my independent variable, I can define it my initial position or my initial time to be any number, and I define it to be 0. All right, plugging and chugging, I get 28.21 meters per second as the initial velocity. Okay, here's a second example. Now, I'm not going to go through all of the steps for you. So what you can do is you can go back and watch the previous example over and over and over until you get it right. But for now, I would like for you to pause the video, go through all of the steps on your own, and see what you get and compare it to mine. Okay, let's get started. So I've got my -90 meters for my y. My initial velocity is 18 meters per second. Okay, my time, I don't know that. So I've got my equation here. Check, I've got my initial velocity. Check. Whoop, wait a minute, I have two unknowns. Darn it, so I can't use this one. So let's go to the y. So if I go to the y, yes, I do have my delta y. I do know my g always. So now I can go ahead and do the same thing I did for the last problem. Solve for my time in my y direction here and plug it in my time here to solve for my delta x. Oh, in this case, time. So when it's all said and done, I get a time of 4.29 seconds. And if you made a mistake, there might be a couple common problems. Number one, don't forget our negative here. And the second mistake might be the algebra itself. Okay, I find that a lot of students understand the physics, but where they go wrong is in the algebra. And I can help with that. Just gotta let me know. All right, here's another one. You've got a Wile E. Coyote, an old 70s and 80s cartoon. I'm not sure they play them very much nowadays, but there you go, have at it. Pause the video and see if you get the same answer. Boom, I get a position of 225.88 meters. Okay, hey, thanks for watching, and remember, if you have a question or in need of help in Phoenix in terms of tutoring, go ahead and give me an email at monroe.watson@gmail.com.